The expectation of a continuous random variable is defined as follows. It is nothing but if you see that when we discuss the expectation of discrete random variable, we had that expectation of the discrete random variable is nothing but the summation of the value multiplied by the corresponding probability. Summation of the value multiplied by the corresponding probability mass function. And in this case, the summation sign is replaced by the integration sign. So it is a continuous thing. So summation need to be replaced by the integration. So the intuitive meaning again is same, that it is nothing but the long run average of the values that can be taken by x. And in this case, we need to check that whether this integration is convergent or not. And for that, again, we need to check whether the absolute value of the whether this integration is absolutely convergent or not. So that's why the expectation exists, provided this quantity is finite. And like the discrete random variable, in this case also, if this integration is infinite, we say that the expectation do not exist. So the definition of the expectation for the discrete and continuous case almost similar, only change is that in case of discrete I have a summation, in case of the continuous random variable I have a integration, in case of the discrete random variable f function is PMF, in case of the continuous random variable the f function is the PDF. Okay, so let x be a continuous. So the definition is as follows: if x is a continuous random variable with PDF fx, the expectation of x is given by this integration, provided this integration is finite. If this integration is not finite, we say that the expectation of the random variable does not exist. Let us take some of the examples. Let us start with the one of the simplest one, when x follows uniform AB. And when x follows uniform AB, you see that if I talk about this definition of the expectation, so first what I need to check whether this integration converges, this integration is finite or not. And you say that in case of the uniform AB distribution, if x follows uniform AB distribution, then the density function, probability density function of x outside the interval AB is 0. So this integration can be written as integration a to b mod of x into 1 by b minus a dx, and I need to check if this quantity is finite or not. Okay, so this integration from minus infinity to plus infinity becomes integration from a to b, because outside the interval a to b the density function is 0, and inside the interval a to b the probability density function or PDF is 1 by b minus a. Okay, so let us check first if this integration converges or not, if this integration is finite or not. And this one is fairly simple. Just we need to think of different cases. The first case when a and b both negative, second case when a is negative but b is positive, and the third case is when a and b both are positive. Okay, and you can include actually equality case here also, that you can put equality here or equality here, does not matter, so that either a equals to 0 or b equals to 0 actually can be incorporated in these two cases. So for a, when a is less than b is less than 0, so both of them are negative, the integration a to b mod of x divided by b minus a dx can be written as integration minus a to b minus x by b minus a dx. So mod of x on the negative side of the real line is minus x, that was basically used, and in this case basically you can easily check that this is given to be a finite quantity. Similarly, when a and b on the both side of 0, then I have to break the integration into two parts, a to 0 and b, a to b. On a to 0 the mod x is minus x, and on 0 to b mod x is x. So again I can proceed as before, and I can check that it is a finite one. Similarly the third case also. And all the cases we have seen that integration is a finite quantity. This integration of the mod x fx dx is a finite quantity, and when so this quantity is finite, and if this quantity is finite, the expectation exists and expectation is given by this integration. So now we have to compute this integration, and if you compute this integration, this simply turns out to be a plus b divided by 2. So when x has a uniform A-B distribution, the expectation of x or average of x is nothing but a by b divided by 2. And note that again this is a very intuitive value. The reason is that the idea of the uniform distribution is that we are not giving any extra attention or extra probability to some interval over the other intervals. So everything is kind of equally likely. So if everything is equal probable or everything has equal likelihood of occurring, then the average should be the middle point of the interval AB. And that's what exactly we got. The expectation is nothing but the middle point of the interval AB. Okay, so this is a quite intuitive value. Let us talk about another example of the normal, which is a very common distribution in practice. So if x has a normal mu sigma square distribution, we know that the probability mass function is given by this expression. Probability density function, the PDF, is given by this expression. So to check whether expectation exists or not, first I need to check whether the integration minus infinity to plus infinity mod fx dx, whether this quantity is finite or not, and we can show that this quantity is finite. How? The showing of this quantity is fairly simple. First I just write what is the density function here, then make this transformation, and once you make this transformation, this integration convert to this integration. Then use the triangular inequality, and you get, and because sigma is strictly greater than 0, you get this part turns out to be this part. Break them out. Mod mu is a constant, come out of the integration. Sigma is a constant, come out of the integration. I have rest of the part inside, and now you see that the first integration exists because of if you do the integration from 0 to some constant z e to the power minus z square by this. So I first talk about this integration, then we will talk about this one, and this integration is nothing but 1 minus e to the power minus z square by 2, and when you take goes to infinity, this goes to 1. So that means this integration exists, and this integration is basically a finite quantity. So this integration exists, this integration finite. Now I have to show this integration is finite. Again, showing this integration is finite is not difficult, because you see that only problem is the infinity. There is no other problem in this, in particular in improper integral. So break it into two parts: 0 to 1, 1 to infinity. 0 to 1 I do not have any problem, and 0 to 1 to infinity. This I can include a z here, which makes the integrand bigger, and this one we have already shown that this one is finite. So this integration also a finite quantity. So both the integrations are finite. That shows that this integration is also finite. So in this case, expectation exists, and as expectation exists, we can calculate the expectation using this integration. And if you do the integration again taking the same transformation, you will find this integration turns out to be mu. Okay, and because this one is basically odd function, that's why basically this integration will be 0. So I get the expectation turns out to be mu. Expectation is of the uniform uniform mu sigma square distribution is nothing but a mu, which is basically the first parameter. Okay, clear? So I hope that this expectation, finding out this expectation, is okay. Let us now consider one of the case for the continuous random variable where expectation do not exist. So let us talk about this density function. You can take this, show that this is a density function, because you need to show only that this quantity is greater than equals to 0. This function is greater than equals to 0 for all x belongs to R, which is straightforward from the expression. And then you need to show that integration of the function over whole real line is 1. And this is also very easy to show, because the integration of 1 by 1 plus x square is tan inverse x. From that one, you can easily show that this integration of this function from minus infinity to plus infinity is 1. That's why this is the probability density function of some random variable assume that that particular random variable is x. And let us talk about whether the expectation of x exists or not, and we will going to show here the expectation of x do not exist, does not exist. Okay, so to show this one, what I have to do, again we have to check whether the integration minus infinity to plus infinity mod x fx dx is finite or not, and that for this density function turns out to be mod x divided by pi into 1 minus x square dx. Now for x lies between minus infinity to 0, mod x is minus x, and for x lies between 0 to infinity, mod x is plus x. Now note that we have problem in both of the integrations. For minus infinity and plus infinity, this integration is an improper integral, and we have problem at near minus infinity, and for this integration we have problem in plus infinity. And what we are going to show here is that this integration itself is not finite. And if I can show that this integration is not finite, that automatically shows that this integration is not finite. In fact, we will be able to show that this integration is not also finite. But even we do not need to show this here, because we will only show that one of the part is not finite. That actually show that both of them will not. That actually going to show that this will not going to be finite. Okay, and showing this one is the standard thing, that we will do the integration from 0 to a, and then take the limit a tends to infinity. So integration 0 to a x by 1 plus x square, I am not talking, I can remove this constant here, because that do not have any effect when we are talking about finiteness or infiniteness of this integration or this integration. Okay, so and in this case the integration turns out to be 1 by 2 log 1 plus s square. Clearly when a goes to infinity, this quantity goes to infinity, that's why this integration do not exist. And that implies that this integration do not exist, and that implies that expectation of x does not exist in this case. Keep in mind one thing, that if I just directly write here minus a to a without this mod, that quantity, that this limit, this integration is basically 0 for all finite value of a, and even if I take the limit of this integration, that will going to be 0, and so the checking minus a to a is not same as checking whether this integration exists or not. Okay, this is a standard thing, and you know that when this kind of integration exists, we say that this integration is conditionally integrable, but this is not integrable. So keep in mind there is a difference between conditionally integrability and integrability, and in this case this integration is conditionally integrable but not integrable, and when we are talking about the expectation, we need to check if it is integrable or not. The conditional integrability we are not checking. Hope these things are fine. So this lecture will stop here. In the next few lectures we will see transformation of random variables.